Front-end development is frequently characterized by the visual, the buttons, colors, and layouts that users see on their screens. Technically, the discipline requires the asynchronous management of distributed state across millions of client devices. This logic must execute reliably on hardware and networks that the engineer cannot directly control. 30 years of computing produced a technical paradox. We moved from typing line-by-line syntax in the 1990s to instructing systems via natural language today. Two continuous bottlenecks drove this entire evolution: the immense computational cost of mutating state and the physical limits of network latency. The resulting explosion of JavaScript frameworks over the last 10 years is a calculated mathematical ladder of abstraction. Each new library was designed to bypass a specific hardware or network limitation. Mastering how we climbed this architectural ladder is required to navigate the current transition. Effective orchestration of AI-generated code depends on understanding the underlying constraints that the models are attempting to solve. In 1995, the web browser was built strictly as a static document reader. It was engineered to parse text and images linearly, making it technically unsuitable for use as a dynamic application engine. This branching tree structure represents the Document Object Model, or DOM. This illustrates the DOM reflow problem. When you use vanilla JavaScript to alter a single visual element, changing a height or adding a class, the browser must recalculate the exact geometry of every other connected branch on the tree. Manipulating the DOM directly through imperative commands forces the browser into constant, expensive recalculations, routinely leading to memory leaks and fragile codebases. In 2006, jQuery introduced the first major layer of abstraction. It provided a unified API that wrapped complex, browser-specific DOM interactions into a single, reliable syntax, addressing the issues of cross-browser compatibility. jQuery successfully standardized the syntax layer, but the underlying architectural bottleneck remained. The browser was still being forced to directly mutate the DOM, which limited application performance. While developers struggled with application logic, they also lacked a basic structural system for layout. Early CSS had no spatial grid. Layouts were built by repurposing float and clear properties, originally intended only to wrap text around images. This 12-column grid shows the Bootstrap solution. It mathematically encapsulated responsive design, allowing developers to organize content by snapping blocks into alignment across different device widths using standardized class names. Web standards often operate on a cycle where native browser capabilities eventually absorb the most successful framework features directly into their engines. Native CSS Grid eventually made Bootstrap's layout system unnecessary. By introducing two-dimensional grid template areas directly into the browser, developers could build complex layouts natively without shipping a large third-party library. Standardizing the visual layout mechanics was a necessary first step. With the presentation layer stabilized, developers could shift their focus toward the logic of routing and application state. Under the traditional model view controller server model, every user action required a full trip across the network. Clicking a link meant discarding the current page and waiting for the server to send an entirely new HTML document. Early frameworks like AngularJS and Backbone.js introduced the single-page application paradigm to bypass this network latency. This comparison illustrates the two models. Instead of the slow server round trip on the left, an SPA downloads a single shell up front. It then uses lightweight JSON payloads to update specific nodes on the client side, as seen on the right. Moving complex business logic to the browser increased the frequency of DOM updates required per second. The client device was now responsible for the majority of the processing. This shift toward client-side logic exposed the browser's physical limit. Direct DOM manipulation, even when orchestrated by a framework, was too slow to handle the demands of application-scale software. In 2013, React moved away from rigid controllers toward composable, isolated functional components. The core of this architecture is the virtual DOM. It is a lightweight JavaScript object residing entirely in memory, acting as an exact mathematical clone of the actual browser DOM. These trees demonstrate React's diffing algorithm. When a user interacts with the app, React updates the memory copy, then mathematically compares this new state against the old state to isolate the exact changes. During reconciliation, React takes only the identified change and surgically patches it into the real browser DOM, leaving the rest of the tree untouched. React did not make the DOM physically faster. It mathematically minimized how often the browser was forced to interact with it, which bypassed the rendering bottleneck. Migrating application logic to the browser carried an unintended consequence. To avoid server round trips, developers forced users to download megabytes of JavaScript before they could view the application. Large payloads saturate the mobile main thread. A mobile processor struggles to parse and execute large JavaScript bundles, leading to unresponsive interfaces and loading delays. This client-heavy architecture degraded search engine optimization and core web vitals, as users and search crawlers often timed out waiting for content to render. Bundlers like Webpack emerged to manage this code. They allowed developers to write modular code that was then compiled and minimized into optimized packages for the browser. Bundlers introduced tree shaking, a method to automatically identify and eliminate dead, unused code from the final package before deployment. Despite these optimizations, the core architecture remained inefficient. Shipping the entirety of an application's logic to the client up front created a persistent performance barrier. Meta frameworks like Next.js shifted the rendering burden back to the server, using server-side rendering. SSR pre-computes the initial HTML on a server. This guarantees immediate visual delivery to the user and avoids client-side rendering delays. Frameworks like Astro introduced island architecture, treating the page as a static document that contains isolated interactive islands. This wireframe demonstrates hydration. The framework ships fast-loading static HTML and only injects interactive JavaScript into specific microcomponents on the page exactly when they are needed. The industry returned to server-side logic, but utilized surgical component precision. The pre-rendered HTML provides the initial view, while JavaScript is reserved only for specific interactive elements. Years of adopting Tailwind CSS for utility styles and React for functional components have created highly standardized, predictable codebases globally. This standardization enables vibe coding, where developers use natural language prompts to instruct AI models to orchestrate these well-documented building blocks. This shows the core architectural shift. On the left, we wrote deterministic syntax line by line. On the right, we manage probabilistic outputs from models like V0. As prompt-driven generation handles the boilerplate, the technical requirement moves toward the integration layer. Engineering now focuses on managing vector databases for semantic search, optimizing token consumption, and architecting workflows where multiple AI agents collaborate autonomously. Human oversight is required for performance tuning, system security, and designing complex systems like micro-frontends. While the model writes the components, the engineer must ensure they fit into a secure and scalable macro architecture. Abstracting the syntax layer has not eliminated front-end development. Instead, it allows engineers to focus on the deepest architectural problems of the modern web.